Bismillah ar-Rahman ar-Rahim. This is lecture 6. We're still on the applications of the Biot-Savart law. This is the case of the circular loop and the solenoid. So consider a circular loop of wire of radius ρ centered on the origin in the xy plane and carrying a current I counterclockwise. Here the field point is P00H on the z-axis. So the position vector of the field point is R, which is ZAZ, which is HAZ, and the source point is a current element at rho phi, or rho and phi prime, and the position vector is R prime rho A rho. So the current element IDL is I rho d phi prime A phi. R minus R prime is HAZ minus rho A rho, so the distance R is the magnitude of R minus R prime, which is square root of rho square plus H square. So we substitute into the Biot-Savart law, which is mu naught I times rho d phi prime A phi cross HAZ minus rho A rho divided by 4 pi times the distance cubed. This corresponds to current element at R prime rho A rho. If we consider the current element at R prime minus rho A rho on the opposite side, then we have dB2, okay. So if we add the 2, we get dB equal to mu naught I times rho squared d phi prime AZ divided by 2 pi rho squared plus H squared to the power 3/2. Now we integrate this from 0 to pi instead of from 0 to 2 pi because we used the two opposite elements. Okay, so it's an only integration of d phi, which is pi, so this would be the result of B, which is in the direction of Z, which is true for all Z, whether it is above or below the xy plane. We next consider the field of a solenoid, which is a coil made by wrapping a wire around a cylinder. If the loops are closely packed, we can consider each turn to be parallel to the loop in the xy plane. So the current distribution picture is then a current sheet with current flowing on the surface of a cylinder of radius A in the direction of phi. Well, this picture shows the current distribution. Okay, so we start with an element which is one loop placed at Z prime instead of Z equal to 0 as in the example before. So we use the same formula for the loop, but now we change Z to Z minus Z prime, okay, which is the position of the general loop. So this gives us dBz, okay, and here the current density is K phi amperes per meter, which is the current per unit width, the width being the Z direction. So if we have n turns per unit length, small n, then for a solenoid of length L and total number of loops or turns, capital N, then the linear sheet current density is K phi equal to Ni divided by L, which is small n times I amperes per meter. So we can calculate the magnetic flux density B on the axis of the solenoid, which we take to be the z-axis, by integrating the field of the circular loop, okay, But here we should use a general loop placed at z equal to z prime instead of z equal to 0, as I said before. So we integrate this over L from minus L over 2 to plus L over 2. Okay. So to integrate, we use u equal to z minus z prime and let u equal to a tangent theta as a substitution. Then du is minus a secant squared d theta, and a squared plus u squared to the power 3 halves is a cubed secant cube theta. So when we substitute back into the Biot-Savart law, we get the integral of minus cosine theta d theta from theta 1 to theta 2. Now the answer will be minus sine theta, okay, from theta 1 to theta 2. Now, from the definition of u, okay, we can calculate sine theta to be z minus z prime over square root of a squared plus z minus z prime squared. Okay, substitute that here. We get this result for Bz. Now, if we have a thin solenoid, okay, for a thin solenoid, the length L is much larger than the radius A, and if L goes to infinity, then Z becomes 0, because any value of Z is just as good as 0, because you look at the solenoid and you see that it goes from minus infinity to plus infinity. So Z can be set to 0, and the result would become much simpler. Bz is mu naught Ni equal to mu naught Ni over L, and this applies also to L much larger than A, and this is the practical formula used for a solenoid. Okay.